that um, none of the possible factors, possible values of R, is a divisor of 23. What assumption are we violating here? This says R is not 2, 3, or 4, and these are the only possible values R could have if R is not 1 or 23. That basically leaves us with no alternative. This leads us to see that our assumption was wrong. Initial assumption was incorrect. There is no choice of R and S in which R in particular is not 1 or 23. In other words, R is either 1 or R is 23. That means exactly that S has to be, in the complementary cases, 23 or 1. Primeness 23 is therefore prime. Let's do a little change of pace. Why don't you get your computer out and crank up Mathematica? If you don't have it or it's not working or something, then you need to get with somebody who does. The process we just went through for 57 and 23 illustrates how, in general, you might go about testing any number, any positive integer, for primeness. You either find some factors or you can't find any factors. And the procedure could be formalized from the example. If I handed you 4,327 and said, is that prime or not? Well, basically what you could do is just start dividing numbers into it and see what happens. You could be very systematic about it. You could divide that by 2, try 3. It's not divisible by 3. No, it's not divisible by 3 either. And there are some makers of Mathematica have devised a function that does exactly that. Basically, you can imagine that it works the way I described. It tests a given integer to see whether it's prime or not. Prime Q, prime query, if you will. So it turns out I picked a number that was prime. You might guess that a number 1 less than that would be not prime. So prime Q is a function in Mathematica that does what we were doing by hand a moment ago. As I say, if you wanted to, you could write a little program to do. This is a question about a prime generating function. I'll put a question mark here because this is what you're going to be investigating. So you're aware that your calculator, and I think I've showed how to do this in Mathematica, can define functions. For instance, we can define f of x to be, say, x squared plus x plus 41. I left out an x, so I'll put that in. So, for example, f of 1 is 43, and so forth. F of 2 is 47. F of 3 is 53. Now, that seems like a function that's just sort of made up. It's not entirely made up. What I would like for you to investigate is the nature of the values of f for x equaling 1, 2, 3, and so forth. I hope you recognize that there's something special about 43, 47, 53. You might just check, if you don't know your multiplication tables too well, that prime q, for instance, of 47 is true. All of these values are true. Raising the possibility of is that f generates nothing but prime values. That might be a conjecture, and you might test that conjecture. And here's how you could test it. Let's make a table of values of this function, just for illustration. We'd like to make a table of x with f of x. First of all, let's do that. And let's do it for just x starting at 1 and going up to 3. If you evaluate that cell, then you get a list of pairs, 143, 247, 353, and so forth. Those are the values of f. Those are the ones we already calculated. Instead, if we go up to 10, we can make a list like this. And the numbers get, of course, bigger. Let's see, 61, I believe, is prime, 71 is prime, 83 is prime, 97, 113, 131. These numbers may be past our ability to sort of tell inspection. But remember the function that we had up here called prime q. What we can actually do is make a table not of ordered pairs, but of ordered triples, where we put in prime q of x. So we'll fix that and evaluate this. And notice that in every case, we get true. If we go up to 20, it's true. Try this out. That's one thing I want you to do. Just simply replicate what I've done here. Don't go any higher than 20 yet. But then on the basis of what you see here, see if you can write down a universally quantified statement suggested by this. It'll be a for all statement. So take a moment and do that. You may want to pause the video. Those two things. And then once you've done both of those things, come back to the notebook here and tinker with this upper limit and see if you can find a value of x for which actually f of x is not prime. And if you do, then go back to your statement and see what that evidence says about your statement. The other exercise that I want you to undertake in just a moment is going to be facilitated by using Mathematica for one kind of, well, easy purpose, but important. You'll notice that we can test out a given number for primeness. We can also ask for the nth prime. So for example, if we say prime 3, that gives us the third prime, which is 5. The 10th prime is 29, and so forth. For the exercise you're going to be doing on the printed pages, you're going to need a list of prime numbers that goes up, well, you have to decide how far. So to see a list like that, it's actually handy to make a table. And you can do a table here very easily. You can make a table just of primes. You'd like to have, say, prime n, and then n is going to range from 1 up to some specified number, like 20, for example, 25. So the first 25 primes are listed here. If you want the first 100 primes, then you can easily get those as well. And you may need those, a list of numbers like that momentarily. If, by the way, you don't like to see your list in a list form with commas in this fashion, you can put it in what's called table form. And one convenient way to do that is to first of all give a name to your list, call this prime list, and then you can ask for prime list to be printed out in table form. And if you don't spell it right, then it won't do it for you. There we go, prime list. So there they are, now made in a columnar form. So maybe that's easier to read, maybe it's not. In any event, happy investigations. I hope you have fun with this. I will see you on Monday. Do save your work in your notebook. I'd like for you to show me what you've got, and if you have any technical questions, I can try to answer those.